Morning Physics 20. Hope you guys are doing well today. Today we are going to look at a topic that has a lot of potential. Yeah, pun intended. Yeah, potential. Yeah. So, and as you can see by the pun on the page with your notes, potential is advertising potential energy having potential. In this case, gravitational potential in the pun. And today's topic is elastic potential energy. So the potential energy that comes from stretching objects out of their normal shape. So we're also going to look at the force it takes to stretch objects out of their original shape as well. And this topic is going to be one that during the regular school year, we would have dappled throughout all over the place. But I think due to COVID, if I remember correctly, in your assignment, I've narrowed it down to like one question on your assignment. So let us begin. All right, so now this thing's not scrolling. There we go, we're scrolling. All right, so ladies and gentlemen, elastic potential energy. This is going to come from any object that is going to be deformed, so have its shape changed. And the key thing is return to its original shape without being completely destroyed is said to have elastic properties. Okay? So these can include all sorts of different things, elastic bands, pole vaulters, poles, springs, a bow, not compound bows. Compound bows don't use elastic potential energy, but recurve and long bows, they absolutely do. Okay? And it's not the string. It's actually the bow itself that bends. It's not the string that bends. Or bends. Of course the string that bends. Stretches. The string doesn't stretch. Okay? So what we're going to do an attempt of artwork here. We're going to draw a bit of a spring. So I was trying to find stuff to help with the lesson, and I took apart one of my pens and I rustled up a spring here. Okay, so there's our spring. At school, I've got a whole box full of springs, and we would have done a cool lab about springs and finding spring constants, and it would be so much fun. But sadly, my springs are at school, and I'm at home, and we're all home, and we're not in physics class, which makes me sad. I wish we were in physics class. Okay, so we've got a spring. That's a spring. It's supposed to be a spring. And we can deform a spring into a couple different ways. You can stretch the spring. Okay. Or, so stretch the spring, which if you're going to take one of the your pen springs and kind of pull it there, when you pull it apart, it's got the potential to do work when it kind of goes back to its original shape there. Or you can compress a spring. Okay. It's supposed to look compressed. I'm not an art teacher. Okay. And either way, when these guys are going to, you're going to let go of that spring, it's going to come back to its original position. And its original position is often called equilibrium. Okay. So, ladies and gentlemen, so when we talk about elastic potential or spring constants, it doesn't have to be elastic bands. It doesn't have to be springs. It can be any object that has elastic properties. Okay. So when you're going to stretch or deform an object, so I've rustled up a few elastic bands. I've got 3 different rubber bands here, which we'll use in our next video, our field trip video. So we have, this is a broccoli elastic band. These are really, really handy. I always keep these. So when you're going to be stretching your elastic band, there is now energy stored in this band. Okay. And it's got the potential to do work when it snaps back to its original position. In that case, it converted into kinetic energy and went slinging across my office. So elastic potential energy converted into kinetic. Okay. So that stored energy can then do work or turn into kinetic as it slings across my office. It's a very good thing Freya was not sitting over there. She would not have liked getting hit with an elastic band. Okay, so our equation for our elastic potential energy, it's not letting me scroll, there we go, is actually very, very similar to our kinetic energy equation. So our elastic potential energy is 1/2 kx squared. Well, look at this, ladies and gentlemen. EK is 1/2 mv squared. So you remember that equation from last year? This equation, the kinetic energy equation, is going to haunt you for the rest of your physics career. This equation we're going to be using in the exact same manner that we'd use this one as far as rearranging. EP is your elastic potential energy, as always, joules. Now, K, this is the spring constant for an object. It's essentially a measure of how much energy, how much force is needed to stretch that object. Now, when you look at the units, newtons per meter. Well, I'll find another elastic band here. I've got 3 of them on my desk. So this one, I don't know if you can see that one as easy. This is the red one. It's easier to see. So with this guy, if I was to stretch this guy 1 meter, it would absolutely snap. But this essentially, it's a measure of the stiffness of that spring, the amount of force it takes to move that spring a certain distance. Okay, and of course, X is the amount of expansion or compression. So it's essentially how far you have stretched your spring. Okay, or your elastic band, or your bow, or whatever it is. It doesn't necessarily have to be a spring. Whatever object that has elastic properties. Okay, so energy is scalar. No direction, please, ladies and gentlemen. Okay, no negative energy. Energy is scalar. Yeah, I know. Repeating the joke from previous video. All right, so we have another equation we're going to look at. So Hooke's law is talking about that force that is needed to expand or compress objects. So Fs as equal to negative Kx. Now, we're going to talk about why we are just going to drop that negative. This is the formal equation, and in all practical uses of the equation, just drop that negative. This is the formal equation. We'll talk about why that is in just a sec. So the force that is necessary to either move the spring or the force that the spring is going to exert is your Fs, and that's in newtons. K is our spring constant. We talked about that, kind of a measure of how stretchy or how stiff that spring or elastic band is. And X is the amount of expansion or compression, so how much you've moved that spring or elastic band or bow or pole vaulting pole or what have you from its original position. Now, we've already talked about this one. K is going to vary per spring. It's a measure of how stiff it is. I'm going to scroll down here. There we go. Okay, so the blue elastic band, which I'm going to get back just 1 sec. Okay, here we go. The blue elastic band, even though it's wider, is actually a lot less stiff than this red one. Okay, so this red elastic band is very stiff, whereas this one's a lot easier to stretch. Okay, so this red elastic band is going to have a higher K value than the blue one. Okay, so, and this thing here is going to vary for each type of spring or each type of elastic or each type of stretchy object. So, and the larger the K, the stiffer the spring, which makes sense when you look at those units. Newtons per meter, the amount of force it takes to stretch a spring 1 meter of distance. So a lot of springs are not going to be capable of stretching a full meter before they break, but so therefore you'd be stretching at a fraction of a meter, and then you would just put your meter as a decimal. Okay. So ladies and gentlemen, now this negative sign, it just implies that it's the force necessary to pull back or restore the spring to its original position. So It's called the restoring force, so it's always pulling backwards. Now, because we can use this equation in many different scenarios, what you are more than welcome to just drop the 0 in your calculations, and then you can use your logic to determine your direction. Oakley dokley? Cool bits. All right, so ladies and gentlemen, let's look at a couple of equations. All right. So before we start with the equations, I am going to make a field trip video when I'm done with this video, and we will use kind of a demonstration with these 3 elastic bands here to talk about spring constants and force and that kind of thing. Okay, so if you want to watch that before you do the calculations, feel free, pause this, go watch the other one, and then come back. All right. So, ladies and gentlemen, a force of 37 newtons. Okay, so we need the force. Use the force, Luke. Okay, is required to stretch a spring 20 centimeters from its equilibrium position. What force is needed to compress the same spring 7 centimeters? Okay, ladies and gentlemen, keyword same spring. That's a key. That means that K is going to be the same for each scenario. Well, I'm going to label scenario 1 as force 1. So in scenario 1, it's taking 37 newtons to compress a spring 20 centimeters. So now x1, now once again, centimeters. We're going to have to convert that into meters. So 0.2 meters is x1 to compress the same spring 7 centimeters. Now x2, 7 centimeters, convert that into meters. Okay. Now, with this, expansion and compression is not going to change any signs with our x, because x is just going to be, well, how far off equilibrium have you moved this? So with the spring that I robbed from a cheap pen in my pen cup over here, I could stretch it like that or compress it like that, and it's still moving off of its original position. And the stiffer the spring, the harder it is to stretch, and the less stiff the spring, the easier it is to stretch. All right. So I've got forces and x's. I don't have k, but ladies and gentlemen, k is the same. I'm going to show you 2 methods for solving this question. You pick whichever method floats your goat. We're going to start with method 1. Okay, so method 1 is I'm going to do 2 sets of calculations using the same equation, but just rearranging them. So, ladies and gentlemen, well, I need to find k before I can find anything to do with my x2. Well, guess what? I can find k with my F1 and x1. So my force, my spring force, the force necessary to squash a spring, is equal to my kx. Okay, is equal to my kx. So, ladies and gentlemen, with this, I can rearrange this to find k. Okay, get it? Okay, okay, yeah. So I'm going to take these numbers and I'm going to plonk them in here. So k is going to equal 37 newtons divided by my 0.2 meters. Note the units, newtons divided by meters. So when you have k, it's going to be a newton per meter. I'm going to plonk that in my calculator, and I'm going to get the value of k as 185 newtons per meter. So to stretch that spring 1 meter, assuming you wouldn't completely wreck it, it would take 185 newtons. Well, I have k now, so I can, in order to determine my F in scenario 2 with that same spring, because the spring is the same, this number is going to be the same, I can take, well, F2 is equal to kx2, and I'm going to take this k, which is 185, and I'm going to multiply that by my x2, once again in meters. And I'm going to wind up with a force of 12.95. I dropped my decimal. Okay, newtons. And then once you round with sig digs, you are going to wind up with 13 newtons. Now it's force. I'm just going to scroll up a bit here. So, and I said force, I did not say magnitude of force. So that means I'm going to want a direction. Okay. What force is needed to compress the same spring from its equilibrium position? Well, we're moving this, if we're compressing a spring, we're moving it back from where it was. So we're not stretching it, we're not moving it forward from where it was, we're moving it back from where it was. So I'm just going to write back as my direction. Sounds good? All right. Now this is method number 2. And once again, when it comes to showing your work, I don't care which method you pick the one that makes the most sense in your brain and rock on, show your work, whatever floats your goat, okay? Either method. So with this method I use the same equation twice in 2 separate steps. Now in method 2, I am going to equate some equations because K is the same. Okay, so the K in scenario 1 is going to equal the K in scenario 2. Well, look how we rearrange this equation here. F over X equals K. Well, I'm going to replace this K1 with F over 1 is equal, or excuse me, force 1 over X1 is going to equal K, right? Well, that's equal to K1. Well, K2 is going to equal force 2 over X2. Okay, just like I've rearranged this equation here. Well, now I don't even have to calculate K, therefore. I don't need the actual number of K if I go through this method. I am now going to rearrange this equation to isolate for F2 by multiplying by X2. And I'm going to wind up with a new equation of F2 equaling F1 X2 divided by X1. Okay. Then with this scenario, I can now plonk my numbers in. The force 1 was 37, X2 is 0.07, and then I am dividing by X1, which is 0.2. And guess what? We wind up with the exact same number of 12.95 newtons, which we then round with sig digs and units to 13. So in this case, either method works wonderfully, and you can go either way you want. This method here, though, is a very, very valuable method that I recommend you guys at least try a little bit on occasion, because this method is going to be 100% necessary in Physics 30, and in a couple of questions up and coming on your assignment. I don't give you enough information to solve the question unless you do method 2 and you are substituting stuff in. So it's a good method to try for when you do need it. All right. Questions? Find me on Google Meet. Office hours. See Google Classroom. All right. So this, ladies and gentlemen, we'll talk this is also a good time to, if you haven't done so yet, pause this video, go watch the field trip video I'm about to film, and you can see this guy. We'll talk more about this using this concept of suspending a mass from a spring using whatever random stuff I have found around my house. All right. So, ladies and gentlemen, a spring with a constant of 55 newtons per meters has a 400-gram mass suspended from it. Okay, ladies and gentlemen, key piece, suspended. Now, that is another way of saying that our velocity is equal to 0. Well, we're dealing with forces. What do we know about forces when we have a zero speed? Speed is 0 meters per second. It means we have an F net of 0 as well. So if we've got no speed, that means we've got no net force. Okay, so what that means, the force of gravity, which is pulling this thing down, is going to be equaling the force that is pulling the spring, equal to the force of the spring that's pulling it up. You know? Yeah. Balanced forces. Woo! So, ladies and gentlemen, let us start by listing out what we got. We've got K as equal to 55 newtons per meter, and we have a mass of 450 grams. And please, no bad grams jokes, guys. You know who specifically I'm talking to. Yes, you know who you are. We're going to convert this into kilograms because kilograms are our standard units for physics, standard SI units. So 0.45 kilograms once you convert your units. And ladies and gentlemen, you've been asked to draw a free body diagram for the stationary object of mass on this string. I got lazy. I drew it on like that on the spring. There you go. I can even draw the object. There we go. There's the object. There's my forces. So we've done A before we even read the question. See, that's the type of habit you guys should be in with free body diagrams. Just draw them. It should be something you just do, whether or not the question is asking for it, because it makes your life so much easier. Trust me on this. Determine the extension of the spring. So that, ladies and gentlemen, is X. So how far X is moving. Well, we know that F net is equal to 0 newtons. Well, if we even have any numerical value for F net, even if it's 0, we can make an F net equation. Yeah, F net equations. Trust me, these are not going away. You need them in Physics 32. Okay, so if you want to take Physics 30 next year, please make sure you're comfortable with that, making F net equations, because it's something we just do as a part of a question. And we just do it. We don't think about it. Okay. All right, so for this one, well, we have the Fs, the spring force, pulling upwards on that mass, and Fg is pulling the mass down. F net is 0, so that means we can get rid of that, and I can add Fg. So my Fs is equal to Fg. So once again, ladies and gentlemen, you guys have two choices here. You are welcome to go and solve for Fg and then equate it to Fs. Excuse me. And then solve for Fs in a two-step equation. You're more than welcome to do that. What I'm going to do, because it's good practice, as for when we're going to be needing the skill later, is I'm going to substitute in the numbers. So Fs I know is equal to xk, and I know Fg is equal to mg. So here, what I'm going to do now is, well, I need to find x, so I'm going to divide that by k. And so x is equal to mg divided by k. And now I'm going to plonk my numbers in. So my mass is 0.45 kilograms. G, as always, ladies and gentlemen, so long as we're close to Earth, averages 9.81. And then we're going to divide by K of our 55. And that's going to give us a lovely value of X to be 0.008 meters. And I wrote an extra 8 in there because it's Monday. It's not actually Monday, it's actually Thursday. There we go. Or if you want, you can write this as still Monday, as, oh, I need to scroll down. Come on. There you go, computer. You can do it. All right. Erase. Back to pen. Or you can write it as 8.00. Goodness, I am really on a roll today. Okay, or 8 centimeters. Both of these have the 2 sig digs. Remember, leading zeros are not significant. So we've got 2 sig digs here, and we have 2 sig digs here, and our units. So the units are different. I don't care which one you communicate your answer as. If you really want, you can also write this in scientific notation as 8.0 times 10 to the negative 12 meters. So either 3 of these are perfectly correct. I'm happy with any of them. Okay, and just because we can, I will show you the method for solving with 2 different equations. So for this one, you would first calculate your FG to be mg, and you would then calculate FG with your 0.45, and you would multiply that by 9.81. And this one, I actually didn't do this method in advance, so I'm going to have to grab my calculator, handy dandy calculator. And so 0.45 times 9.81. And I'm going to wind up with an FG of 4.4145 ... I'm going to equate that to my Fs because Fg equals Fs. Therefore, Fs is going to equal 4.4145 ... newtons. So then I could rearrange this. So my Fs divided by my K is going to equal X. And so then once you put your numbers in of 4.4145 ... and then you can divide that. Actually, there are no dots. That's actually the exact number in my calculator. Habit with the dots. And then the K is 55. So then you just divide 55 in your calculator. And guess what, ladies and gentlemen? You wind up with the exact same answer. So either way, either method is fine. Show your work. Units, sig digs, use appropriate physics principles. I don't care which method you use, but it is just a good one to make sure you do know how to do this for when the scenario means you have to do it. Okay, because there are going to be some of those at some point. All right. So, ladies and gentlemen, last question for today. This video is a little bit shorter. We've got, shorter when I'm considering my videos can sometimes be over an hour. I think my Physics 30 lesson, my most recent Physics 30 lesson is definitely over an hour video. You guys are troopers. All right, so the amount of stored energy in a spring is 19 joules. All right, so that would mean that's our energy. Note our units of joules, and that's the energy that is stored in that spring, its potential energy, so 19 joules. If the amount of expansion or compression was reduced to half of its original value. Here we go, ladies and gentlemen. This is what I'd love to call math wizardry, although it's really substitution. So this is how we're a very, very important skill that we do all the time in Physics 30. And we've done a little bit of it here, but not really. So if you want to take Physics 30, please, please, please pay really close attention here because we do this all the time in Physics 30. Okay, so that means, well, if the amount of expansion or compression was reduced to 1/2 of its original value. Okay, so that means, I'm just going to write that as a half there for now. So half of its original value. Our x prime is going to equal to 1/2 of original x. Now, prime, ladies and gentlemen, means after. And x is what it's originally going to be. What would be the new stored energy of the same spring? Okay, so this is going to work. It's going to get a little bit tricky. I'm going to break this into 2 different cases of original and modified. Okay, let's visualize this a bit. So I got my blue elastic here. Now, it is stretched to kind of the width of my camera here. You see, I've got to stretch the width of the camera view. I'm now going to reduce its stretching to kind of about half of your view screen there at the bottom. Okay. So what I have done is I have gone and reduced the amount of stored energy. but it's not going to equal exactly half that energy, okay? So when you look at that equation, it's a squared equation. Now, my EP is equal to 19 joules, which means that 19 joules is going to equal kx squared, because 1/2 kx squared. There we go. Okay, drop my half. So 19 will be equal this amount. This set of numbers here is going to equal 19. That's going to equal EP. Okay, so ladies and gentlemen, I'm actually going to write that a bit nicer because that is a bit of a disaster. So 19 joules is also equal to 1/2 kx squared. It would help if I wrote the letters in the right spot. Goodness gracious. That's better. Right numbers, right variables, right spot. All right. Now, in the modified equation, I'm trying to find EP prime. Now, remember what I mentioned earlier, prime means after or modified, okay? So I need to figure out, well, what is it? I know that my x prime, so my modified x, is half of what it was over here, okay? So what I'm going to do is I'm going to write it as x over 2. Okay, so I'm going to write it as a fraction. So this is where you guys do need to know how to work with fractions, guys. It does come into play really handily. Okay, I know fractions are kind of a nuisance, but it's a really good skill. Okay, as much as we bitterly complain about fractions. All right, so now what I'm going to do is I'm going to do some substituting here. Well, if x prime is equal to half of what x was originally, my EP prime is going to equal 1/2 k. And now I'm going to take that x squared. You see this x squared here in our equation. And I am going to substitute that x with x over 2 squared. Okay. So, ladies and gentlemen, now what I'm going to do is I'm going to do my best to solve for this here. Okay, I'm going to solve what little I have. So EP prime, I can't do anything with that f. I can't do anything else with the k, but I can solve this. X squared, x over 2 squared. Well, remember when you have something squared, an exponent on the outside of the bracket, what it actually is going to be x squared over 2 squared. Okay, because I have to bring that squared onto each of those values there. So my EP prime is going to equal 1/2 times k, which is going to be x squared over 4. Okay. Well, ladies and gentlemen, I got to get rid of that 4. I'm going to rewrite this. Well, what's the same as dividing something by 4? Multiplying by 1/4. So I'm going to rewrite this. So EP equals 1/2 k x squared times 1/4. Okay, so I've just taken this divided by 4 and I've turned it into multiplying by 1/4. I've just kind of separated it out. I factored it out a bit. Okay, now we can solve this, ladies and gentlemen. Okay, I'm going to move this up here. Draw a line there. So my EP is equal to 1/2 kx squared multiplied by 1/4. Well, look what we have now, ladies and gentlemen. We've got this here, 1/2 kx squared. I forgot my primes. There we go. And this is the original, 1/2 kx squared. 1/2 kx squared is equal to 19. Guess what? I can substitute this whole kit and caboodle for 19. So EP prime is equal to 19 joules times a quarter. So plunk that into your calculator, ladies and gentlemen, and you are going to get the lovely value of 4.75 joules. That's 19.0, so I want 3 sig digs. Okay, so ladies and gentlemen, because x is squared, you're going to wind up with not half the energy, but a quarter of the energy that it was originally. So I know math wizardry is really tough. We're going to do it. We do a lot of it in Physics 30. We do a little bit of it here. This is just, so if you want to take Physics 30, definitely do some practice with that one. All right, so ladies and gentlemen, we've got a bunch of practice problems here for you to do. We've got the ones from your workbook, and we've got some ones here. Give some of those a try. And if you haven't watched the next video on if the field trip video for this, give that one a watch, and I'll talk to you guys later. Have a good day. New fires, injuries, or solutions.